Okay, quick little review. We know that a sequence can be thought of as a function where the domain, the set of possible input values, is the index, and the range, the set of outputs, is the terms of the sequence. So when we're writing the sequences, we've been writing phrases such as the nth term or the previous term or the term before that or the position of the term in the sequence. Algebra offers a more direct way of describing sequences. One of the big ideas of mathematics is notation, a consistent, compact way of writing and working with mathematical ideas. For example, algebraic notation can represent the expression 10 and something to be multiplied by something minus 10 as x plus 10 times x minus 10. This notation makes it a lot easier to understand what you're trying to say than the garbage that I just read to you. Angie needs to show you something wonderful and amazing. Oh, would you look at that? That's my future son-in-law right there. Can you imagine? Okay, so another thing you need to know as we're starting this section of the lesson is subscript notation. Subscript notation is written below the letter, the variable that we're dealing with. So a subscript n, a subscript 1, a subscript n minus 1. An exponent that's written above a letter is called a superscript, like Superman. Subscripts are below the letter, like subbasement. There are two different ways to refer to a specific term in a sequence. There's function notation and subscript notation. Function notations for sequences are exactly the same as for any other function, f of n. F is the identifier, n is the index. As with other functions, the letter f is a common identifier, but any letter can be used. Any letter can be used for the index too. So for example, you could use P of Z for a sequence that represents the postage of a letter as a function of the number of ounces. A subscript is anything written below the line, usually after another number or letter. In mathematics, subscripts are used for lots of things, including a sequence or a series of related or numbers. Subscript notation looks like this, where A is the identifier for the sequence and the subscript is the index, n in this case. The subscript here is pronounced A sub n or A subscript n. Sub n is just faster. The letter A is a common identifier, but any letter can be used for the identify or the index, so it could also be PZ or anything else. This is a lowercase p. It's hard to tell because I don't have lines on my page, but it's a lowercase p sub z, not capital P and then lowercase c. Okay, lowercase sub z. These two notations represent the same thing, f of n and a sub n, or P of Z and P sub Z. It's just two different ways of writing the same information. Typically, the index begins with 1, but there are times when it may make sense to start with a 0. This table shows the two different ways to write the same information. This is function notation, this is subscript notation for 5 index items. So given the following sequence of 496, 162, 54, and 18, write an expression in subscript form for fourth term of 18. Use a sequence identifier of A. Explain each part of the expression. In subscript form, it would be written as A4 because it's 1, 2, 3, 4. It's number 4. It's the fourth index item in this sequence. The letter A is the sequence identifier or name of the sequence. It told us to use A. The subscript number 4 is the index, meaning that 18 is the fourth term. So this is your answer. Consider a sequence identified as K using an index of Q. And then I want to know function notation and subscript notation. So I gotta scroll up, I can't remember the words right now. Function notation is K of Q and the subscript notation is K sub Q. Let's work through this example together. Write a formula in which the nth term equals the index multiplied by 2.5, then decreased by 3 in both function notation and subscript notation. So let's go through and look at the terms first that we need to understand. Multiplied is obvious. We're going to multiply. Decreased means subtract. Whoop! Okay. Decreased, we're going down in value, so we're subtracting. So if the rule is to multiply the index by 2.5, then subtract 3, we need to figure out where the index is first. The index is n. Okay. So we're going to write in function notation first. The words tell us that we're going to, if we're doing function notation, we're starting with f of n is equal to multiplied by 2.5, so n times 2.5, then decreased by 3, minus 3. So you start at the beginning, work your way through step by step. N multiplied index, which is n, multiplied by 2.5, decreased, subtract by 3. Okay, so that's function notation. Now we need to do subscript notation. So subscript notation starts a sub n is equal to the exact same information, 2.5 times n minus 3. These are equivalent. They mean the same thing. They just have function notation and subscript notation. You can use either of these to find whatever information you need to. So if you want to find the 7th term in this series, you would just substitute 7 for n. So substituting 7 for n and solving it, we find out that the 7th item in this index, 7th term, is going to be 14.5. This makes it really easy to figure out whatever term you want without having to make a table and figure out every single term. Let's work through this example together. What if the terms in the sequence are defined using a previous term? If the 10th term in a sequence can be written as a sub 10 or f of 10, what is the 9th term in the sequence? Well, this is tricky, except we don't have to sit here and figure out an actual number because we don't have all of the information to get an actual number. It's just this easy. The answer is either a sub 9 or f of 9 because that's the 9th term. But what if we have even less information than that? If the nth term of a sequence can be written as a sub n or f of n, what is the term just before the nth term? We're going to have to treat the variable as a variable because we don't know what the number is. The answer is either a sub n minus 1 because we don't know what n is, or f of n minus 1. Write an expression for the term before the nth term using both function and subscript notations. So this is confusing for me and my non-math brain. We know we have the nth term, okay, and they want to know, here's n, now we want before that, and then we want before that, okay, so it's back 2, okay. See if you can write that formula. The answer in function notation is f of n minus 2. In subscript notation, it's a sub n minus 2. I'm sitting here sighing, dreading starting this video again. Up to this point, I feel like I've had a grasp on this and feel pretty smart, pretty confident, like I got this. Okay, things are about to kick off. Consider the prices that the U.S. Postal Service charges for first-class letters. On July 10th, 2022, they charged 60 cents for the first ounce and 24 cents for each additional ounce or fraction thereof. Can you write a recursive formula for this sequence using function notation? It will have two parts, an equation for the first ounce, an equation for each additional ounce. Then can you translate the formula to subscript notation? Can you use either formula to find the postage for a 3-ounce letter? Holy cow, that's overwhelming. Okay, let's go through this together. I'm very overwhelmed. We're going to start with just this much and see if I can work through it. This makes sense. This is the formula for the first ounce. F of 1 is equal to 0.6 because for the first ounce they charge 60 cents. I got that. I'm good. Okay. For each additional ounce, f of n is equal to f of n minus 1 plus 0.24. Okay, each additional ounce makes sense to me. The plus 24 makes sense to me. But this n minus 1, I'm kind of struggling with. So this is the index number. So I guess it's each additional ounce. So like if we're on ounce 2, then it would be 2 minus 1, which would be 1 ounce, plus 0.24. So our second ounce, I'm confused how they got here because that would be 1.24 on the second ounce, but it should only be 0.6 plus 0.24. So I'm very confused. I'm not sure how they got this formula. Hopefully, we'll be able to figure this out. So now they're just converting this over to subscript notation. So it's a sub 1 is equal to 0.6 and a sub n is equal to a sub n minus 1 plus 0.24. I'm still not sure where this n minus 1 is coming from. I'm very lost on that. Part of my issue is that when they were teaching us math in the 80s and 90s, they just said, because that's why. It's n minus 1 because of that's why. So at this point, I'm just going to continue with because that's why, because that's what goes there. Okay, and we're going to see if we can continue to figure this out. Then the final thing it wanted us to do was to find the postage for a letter weighing 3 ounces. So it says that the first thing we need to do is to find the cost of a letter weighing 2 ounces. Why? I have no idea. It told us to find a letter weighing 3 ounces. But okay, we'll solve for a letter weighing 2 ounces. Sure, why not? Okay, so using our function formula, we're just going to plug in 2 for the value of n. Okay, so we have f of 2 is equal to f of 1 because n minus 1, which would be 2 minus 1, is 2 minus 1 is 1. So we end up with f of 1 plus 0.24. Okay, so that's how we got this up here. Now we know that f of 1 is equal to 0.6. So this is 0.6. We drop down the 0.24. We add those together and we get 0.84. So a 2 ounce letter costs 84 cents. Okay, so now we need to find the price of a 3 ounce letter. Now why we had to find the price of a 2 ounce letter, I have no idea, because it's doing nothing with the 2 ounce letter, but you know, fine, whatever. Let's find the price of a 3 ounce letter. Okay, I guess I see why they wanted us to find how much a 2 ounce letter weighed. I don't know. For a 3 ounce letter, we're going to substitute 3 in for n. So f of 3 is equal to f of 2, because it's n minus 1, so 3 minus 1 is 2. F of 2 plus 0.24, f of 2 is equal to 84 cents. So 84 cents plus 24 cents is $1.08. So f of 3, a 3 ounce letter, is $1.08. It can also be written as a sub 3 is $1.08. Okay, we're going to do this one together too. It says, translate this sentence into both subscript notation and function notation. Each term in the sequence is the product of 7 and the difference of its index and 1. So first off, define all of the math terms. Product means multiplication. Difference means subtraction. Okay, if you can get that figured out first, it's going to help a lot when it comes down to writing the formula. So let's see here. We're going to start with function notation just because I prefer that. This is what the formula is going to look like. I'm going to walk you through how we got here. So it says each term in the sequence. So that tells us f of n or a sub n. Each term in the sequence. Okay. Then is the product. So we know that we're going to have an n over here, and we're going to have multiplication, okay, of 7. So we have 7 as part of the multiplication, so 7 times n. and the difference of its index and 1. So we have the index minus 1, which means this needs to be in parentheses and multiplied by 7. Okay? So if it said just the difference of 1, we would not have parentheses. It would be 7n minus 1, no parentheses. But because it says the difference of its index and 1, n and 1 need to be in parentheses. So this is how you come up with this formula. That's how it's written in subscript notation. All right, this is our last page. Hopefully we can get this figured out and I can actually help you with this. A sports tournament competition starts with 32 teams. After each round has been played, only half the teams remain. This is called a single elimination tournament. This situation can be represented by either of the following equivalent formulas. The explicit one says T sub r is equal to 32 times 0.5 to the power of r minus 1. And the second one, the recursive, is T sub r is equal to T sub r minus 1 times 0.5. So I'm just going to say at this point, it's just r minus 1 or n minus 1 because that's what it is. Just accept it, deal with it. It's fine, okay? I think it's because we're trying to get the number before the number that we actually want, if that makes sense. Because like before, they wanted us to find a 2-ounce letter when really we want to find the 3-ounce letter. I guess you have to find the 2-ounce letter before you can actually find the 3-ounce letter. So what we're going to do with these is describe each part of the notation in the context of the situation, and then rewrite both formulas using function notations. Use the same letters for identifier and index. So this one actually shouldn't be too hard because we just have to describe what's going on here and then rewrite it as function notation, and that's actually really easy. So pause the video, go over it, then come back and we'll see what we can do. Okay. So the letter T is the sequence identifier. It represents the number of teams playing in each round. R represents the round being played in the tournament. Beginning with the first round, R equals 1. It is the subscript to the identifier T as well as a part of the exponent for the number 0.5. The number 0.5 is used since only half of the remaining teams continue to the next round. Okay. And written in function notation, it is T of r is equal to 32 times 0.5 to the power of r minus 1. And when T of 1 is equal to 32, then T of r is equal to T times r minus 1 times 0.5. All right, this is the last problem for the lesson, and then we'll go over the practice questions, and we're done. So consider the following recursive formula for the population of bacteria P over a number of days D. It says if P1 is equal to 100, then the P sub D is equal to 2 times P sub D minus 1. Rewrite this formula in function notation using the same letters for identifier and index. Pause it, do it, come back. All right, in function notation, it is P of D is equal to 2 times P parenthesis D minus 1. Let's go to our practice questions. Now, some of these I can't remember because I was doing this video yesterday, the other parts of this video yesterday. So I'm going to do questions 3, 4, and 5. I don't know if I did 3 and 4 already. I hope I did because they are from a different part of the lesson. Sorry about that. Oh wait, I do remember because these were the weird fraction ones. I did do 3. I'm going to assume... Oh no, okay, I didn't do 4. Okay, so let's do question number 4 on the practice. It says, given the first 5 terms of the sequence 3, 7, 11, 15, 19, determine which option is the correct subscript notation for the explicit formula. A sub n is equal to 3 plus 4n, a sub n is equal to 4 plus 3n, a sub n is equal to negative 1 plus 4n. So let's look at our problem, pause it, solve it, come back. Okay, so what I did is I just stopped and I looked at this pattern and I quickly figured out that the common factor, the constant, sorry, between each of these numbers is positive 4. 3 plus 4 is 7, 7 plus 4 is 11, 11 plus 4 is 15, 15 plus 4 is 19. So I'm sure there's a more official way to figure this out, but what this tells me is that the constant has to be 4, and there's only one of these problems where the constant is 4, and it's this one. So that means the n would be 1, because 3 times 1 is 3 plus 4 would be 7. So it doesn't matter about the rest of it. All we need to know is that the constant has to be 4. So this is your answer. This is question 5 on the practice. Given the first 5 terms of the sequence a sub n is equal to 2, 6, 18, 54, 162, determine which option is the correct subscript notation for the recursive formula. There's if a sub 1 equals 2, that's for all of them. Number 1 is a sub 1 is equal to 3a sub n minus 1. Number 2 is a sub n is equal to 3a sub n plus 1. And option 3 is a sub n is equal to 3a sub n minus 1 plus 2. Go ahead and pause it, figure it out, come back. Okay, how I solved this was I looked at the pattern and I could see that it wasn't going to be addition subtraction because this difference is 4 and this difference is way greater than 4. So I started doing division. I did 6 divided by 2 is 3, 18 divided by 6 is 3, 54 divided by 18 is 3, 162 divided by 54 is 3. Yes, I used a calculator. There's nothing wrong with that. Okay, so knowing that, we know that it has a nice constant at 3. Okay, we don't need to have anything beyond that. We just need a multiplication. It's fine that way. Coming down here, we know that our magical answer is always n minus 1. So this one's out because it can't be n plus 1. Goodbye. We know we don't need anything past just the multiplication, so we don't need this one. It has to be this one. Question 4 on the quick check wants you to do the same type of thing as does question 5. Let me look at real quick and just double check. Oh, okay. Question 4 wants you to use the terms in the sequence to describe a 7. I hate when they do this, when they make it completely different from the practice. The practice builds up your self-esteem, makes you be like, yeah, dude, I got this. And then they do something completely different on the quick check and make you fail. So this is the sequence they give you, and they want to know what the number is going to be for a sub 7. So we have 1, 2, 3, 4, 5, and then we need to figure it out for a sub 7. You can see here that the difference between each of these numbers is minus 4, so our constant is going to be minus 4. So from here, you're going to create a formula. So I started writing the formula and figuring all of this out, and then I realized I was doing this the hard way. I am all for working smarter, not harder. It already gives us 5 terms, and we're only trying to get to 7. We know what the constant is, so just subtract form. That'll give you the 6th term. Subtract another 4. That'll give you the 7th term. There's your answer. Yeah, I'm teaching you how to do it the easier way instead of the correct way, because guess what? It's still going to give you the right answer. The last question on your quick check just wants you to take a subscript formula and change it into a function formula, which is really easy to do. I believe in your ability to do that. Okay, guys, good job. Lesson over.